Yeah, the recording will start here. We haven't covered any physics or anything like this. We've just talked about the structure and the symbols. That's nothing particularly difficult about that. All right. Here's the beginning, talking about the structure of a discrete NMOS and discrete PMOS. Then we have our CMOS or complementary MOS structure. Depicted here, we have a twin well process. Then we have our schematic diagram symbols, and the arrows indicate which pairs go together. All right, reviewed. So now we're going to talk about MOSFET characteristics. So all of this analysis is going to be from the perspective of us looking at an NMOS device, much like we looked at an NPN device or NPN BJTs, figured out how all that works, and then we're like, okay, well, PNP kind of works the same, but we flip the letters. It's going to be pretty similar to that. Okay. So the first thing that we're going to talk about is the threshold voltage. And I literally cannot remember if threshold voltage is supposed to have two H's in a row or not, but it looks weird to me, so I'm just going to put one H and you'll know what the hell I'm talking about. All right, so let's consider a simple NMOS transistor that is connected to some external voltages shown below, right? So here is our substrate. Here we have N plus implant, N plus implant. This is our source. We're going to tie our source to ground. This is our drain. We're going to, tie our drain to ground. Here is our gate. We are going to apply some voltage at the gate where VG is going to be a little bit greater than 0, right? And for the sake of argument, our body terminal would be at ground as well. All right, so with our source and our drain at 0, if we apply some small voltage to our gate, I'm going to label this as P sub down here, what do we expect to happen, right? So effectively, we have put a positive voltage on our gate terminal with all other terminals grounded. Any free electrons in this metal are going to get attracted to the positive polarity terminal of our supply voltage, which is going to leave behind a positive charge on our gate. So we are going to have some charge here, Q plus, and this positive charge is going to attract any minority electrons from our p-type substrate material, right? So minority electrons, which I think I've been using blue for, are going to get attracted into the region underneath the gate such that we have some net amount of negative charge. So what is this? Parallel plate capacitor is exactly what it is. We have voltage control over the amount of charge. So we have a parallel plate capacitor where our capacitance, we're going to call this the oxide capacitance, Cox, and I'm putting a prime here because this is actually going to be the oxide capacitance per unit area based on our dimensions, is going to be the permittivity of the oxide divided by the thickness of the oxide layer. So that's epsilon sub ox divided by T sub ox, where T sub ox is the thickness of our oxide layer, usually on the order of nanometers, tens of angstroms kind of things, which is just a fancy way of saying nanometers, usually very, very small. Okay. For most devices, this oxide capacitance per unit area is going to have a value in the femtofarads per micron squared regime, or possibly even attofarads per micron squared. So it's a very, very small capacitance. And in order to use a MOSFET as a capacitor, it needs to be huge. Yes.
Going back to your diagram, I know we talked on that you have P substrate and a P plus layer.
What do you mean by layer?
Or like you see how we have the P quantity in the body?
All right, so let's go back to this. You were talking about.
Okay, we only have a P plus there.
This P plus thing right here is our body connection. It is there to make sure, so we're depositing metal here, and then we have a lightly doped semiconductor. We put this highly doped semiconductor so that there's a transition from highly conductive semiconductor to lightly conductive semiconductor, so that this is an ohmic junction effectively, and this is also an ohmic metal semiconductor junction. If we tried to put metal directly on the lightly doped substrate, we wind up with a rectifying contact, which is not what we want. We don't want a diode anywhere in this thing. This is a field effect transistor, not a junction transistor.
Okay. Now going back to the MOS, why do we not have plug that body? The one we just did.
Okay. I forgot to put the plus sign. The same purpose, doesn't matter. All right. So we have some capacitor thing here going on, right? So effectively, as our gate voltage gets larger and larger and larger, we are going to attract more and more minority carrier electrons into that channel region until we hit a point called strong inversion, okay? So this process overall is called inversion because the p-type region directly beneath the gate area is gradually becoming n-type. So strong inversion occurs when the channel formed by the minority carrier electrons becomes as n-type as the substrate is p-type. So we are going to consider strong inversion as the threshold of being able to use this device for anything. So until strong inversion occurs, we're effectively saying that the device is in cutoff region where no current is. Technically, that's not true. There are sub-threshold operational relationships and all of that kind of stuff that if you choose to go to graduate school and really do deep dives into this stuff, you'll learn about. Effectively, it's just saying you're going to get really, really small currents because there's not a whole hell of a lot of free charge carriers there to move around, right? So some current will flow, but it's going to be so small. For the purposes of this class, we're saying this device doesn't turn on until strong inversion occurs. And this strong inversion occurs at a very specific voltage, which we are going to call the threshold voltage. And so now you guys have to remind me of what symbols that we've used in this class before. Because we have Thevenin voltage, which is commonly VTH. We have a thermal voltage, which some people call VTH. And now we have a threshold voltage, which is also called VTH. So, and sometimes we'll have multiples of those in the same damn circuit because this has to be as confusing as it can possibly be, okay? So I am going to adopt this convention from here on out, okay? So this is a quick aside type thing. I'm going to explicitly write out Thev for a Thevenin voltage. VT will be thermal voltage, KBT over Q, and then VTH will be threshold voltage of a MOSFET. I am 100% sure that sometimes I'm going to accidentally capitalize the H and other times I'm going to leave it lowercase. If I'm just saying VTH, I mean threshold voltage from here on out. And if you ever have a question, just ask and I will clarify. Okay. So our threshold voltage, damn it, I literally just put capital letter here, is the work function of the metal semiconductor junction. So this is difference in work potential of the metal and semiconductor plus twice phi f where this is the contact potential of the substrate plus the square root of 4 times Q times the permittivity of our substrate absolute value of phi F times the doping level of our substrate. And then, actually, hold on. This big square root thing is divided by the oxide capacitance. So this big ugly thing here in the numerator, what does it represent? So we have difference in potential. So that's a voltage. Contact potential, also a voltage. And then we have something divided by capacitance. So what does that something have to be? Charge, exactly right. So that's literally just the charge we pulled into the channel region. Okay. Yes.
On the difference.
MS for metal semiconductor. So if we go back to our picture, effectively we're saying there's a small voltage drop because we have a metal semiconductor junction, and then a small voltage drop because we have a change in conductivity between this implant and the substrate. And then there's a voltage drop because we have a capacitor here. That's literally all it is. It's this voltage plus this voltage plus the voltage drop across that capacitor tells us what our threshold voltage is when we've pulled enough charge in to make the channel as N-type as it was P-type before. All right, so threshold voltage taken care of. Effectively, if our gate voltage is not greater than our threshold voltage, our device is off. No currents flowing anywhere. Now let's talk about body effects. So, starting with our NMOS transistor again. P plus, N plus, N plus. Source will be grounded. Drain will be grounded. Our gate voltage is greater than 0. And let's make our voltage applied at our body terminal less than 0. What's going to happen under this situation? Okay. So we have a PN junction around our implants, right? Because we have an N region in contact with a P region, we have a PN junction. If our body terminal is negative, is this junction forward biased or reverse biased? It's reverse biased, which means we're going to have a larger depletion region that we have to deal with, right? So if we have a larger depletion region, we have more charge stored in our depletion region. And effectively, it's going to make it harder for us to move minority carriers into the channel region. So what we're going to see is that our threshold voltage winds up becoming larger, because it's harder to make strong inversion occur. Okay. Mathematically, our threshold voltage will become VTH naught. So this is the threshold voltage when body effects are not present that we just talked about, plus gamma times the square root of our substrate contract potential plus the potential difference between our source and our body minus the square root of just our substrate contact potential. Gamma is the body effect parameter or coefficient, whichever floats your boat. And its value is the square root of twice Q times the permittivity of the substrate times the doping of the substrate, all divided by our oxide capacitance per unit area. And typically speaking, from 0.3 square root of volts to 0.4 square root of volts. So the more negative we bias our body term, the more pronounced the body effects are going to be. And it literally just serves to effectively make the threshold voltage larger. And then we're going to see, particularly when we look at a small signal model, that can have some impacts on some things as well. All right, Ryder.
What?
Body coefficient. Oh, I said body efficient. Let's put co in front of that because that seems weird. My bad. So let me write this out. I actually just combined effect coefficient into a single word and made it look awkward. Body effect coefficient. Thank you for that. Okay. So now let's delve into the interesting stuff. What happens when we allow the source or the drain to not be grounded out? So effectively, what happens when we try to get some current flowing through this thing? So actually, that brings back another thing really quickly here. In our schematic diagram representations and all of this kind of stuff, our device current or our drain current is shown as a current that flows from the drain to the source. I didn't put it here, but in this one, it'll flow same direction down from the source to the drain. When we were talking about this particular picture right here, where our source and drain are both shorted to ground, even if our gate voltage is high enough such that we've gone beyond or met our threshold voltage or gone beyond our threshold voltage, we shouldn't see any current flowing in the device, right? So even though it's on, it's still just really acting like a capacitor. And the reason for that is because our current flows from the source to the drain or from the drain to the source, depending on if we're dealing with positive charge carriers or negative charge carriers. And if there's not a potential difference between the source and the drain, we shouldn't see current getting pushed in one direction or the other, right? That's the field effect of the field effect transistor. We need an electric field established either in this direction or in this direction in order to have charge actually travel in a net direction through the channel, okay? And so what we're going to talk about now is how that works. So this will be, we're going to start things off. Let's just call it MOSFET current voltage characteristics. Okay. So let's say that I had a bar of semiconducting material like so, and I'm just attaching wires to it so that I observe some current I flowing from left to right through this semiconductor material. If we have some charge density measured in coulombs per meter, and the velocity of our charges measured in meters per second, we would find that our current is literally just the product of our charge density times our charge velocity. We wind up getting coulombs per meter times meters per second, comes out to be coulombs per second, or current in amperes, right? So let's see how this applies to an NMOS transistor. So we've got our substrate down here. I'm going to try to draw this a little bit more 3D actually. Just giving myself room to do so. So let's say we've got something like this. So here is our N plus implant, another N plus implant, and then these extend into the page. And then I'm going to put my metal plate on top like so. So this is my gate terminal. Here's my drain terminal. Here's my source. And then over here will be my body. Like so. Let's start off with everything grounded once again. And our gate voltage is equal to our threshold voltage, which means we have a thin layer of electrons between our source and our drain directly underneath our gate terminal, right? So because the onset of inversion occurs when the gate voltage is equal to the threshold voltage, the inversion charge density produced by the gate oxide capacitance has to be proportional to VGS minus VTH. So effectively, if we exceed the threshold voltage, our charge density, we're going to accumulate more charge. And our total charge density here should be W effective times our oxide capacitance times VGS minus VTH. Let me put this as a lowercase h, and then let me define what our width is. So our width is our dimension effectively into the page, orthogonal to the direction of our channel. So if we were to increase our drain voltage, what do you think would happen? So if we apply some positive voltage to our drain, now let's think about things, okay? So effectively, if we look at this as a capacitor, we have some large voltage with respect to ground here. And then we have some voltage with respect to something that's above ground on the other side. So what we should see is that our charge distribution should actually change shape, right? So we are going to have more charge stored underneath the gate on this side and less on this side because the potential difference is smaller, right? So the amount of charge, the amount of charge stored on a capacitor is proportional to the voltage drop across the capacitor. If the voltage drop across the capacitor is smaller on one side than it is on the other, we should see that there's less charge on one side than the other. So instead of having a nice flat charge distribution, instead it's going to be slanted like that to take into account the potential difference across the channel. So let's define an axis here. So this is our origin. This is our effective length of our channel. And then in the middle here is X. And so we should see that our charge distribution is now dependent on position. Right? So it'll come out to be QD will be equal to our effective width times our oxide capacitance times VGS minus the potential at location X minus our threshold. So when we're on the gate side of things, this potential is effectively 0. And when we're on the drain side of things, this is much larger. And so we see that we have less charge. Yes. So it is different. It's the same quantity, but now we're taking, it's not measured in capacitance per unit area. It's just the overall capacitance. Okay. So we're taking into account the entire area of this thing here, which would be the effective width times the effective length. So not capacitance per unit area, just capacitance. Yes.
So if you have the form access to the area,
I think the short answer is yes. You should have probably done something in your field theory class like that about what happens if you have one plate that is flat and the other plate slightly askew. You can do it by integrating, or you can do it by effectively slicing it into very small capacitors that are connected in parallel, each having a slightly different gap distance, which is actually probably easier than the integration will wind up being. Yeah. All right, so let me put this as at VD. Actually, 0 volts is less than VD is less than our threshold. So we're going to have this linear distribution. We're actually going to have a linear distribution, charge distribution when VD is greater than VTH, but that's going to cause some interesting things to happen that we'll talk about probably on Monday. All right, so our current is going to be negative the effective width times the oxide capacitance times VGS minus our potential at X minus our threshold voltage times the velocity of our moving carriers. And this negative sign is coming from the fact that our X direction is defined from left to right, but our current is going to be flowing, or positive current is going to be flowing from right to left. So that negative sign is just taking into account that the X direction, or the direction of current flow, is opposite the direction of lowercase v here is velocity, uppercase V here is an electric potential. Well, another confusing V's all over the damn place. Okay, so going way back to our first or second lecture, the velocity of a charge carrier in a semiconductor is nothing more than the mobility times the applied electric field. So since V is equal to mu times electric field, and electric field as a function of position is just negative the derivative of voltage with respect to position, we get our drain current to be our effective width times our oxide capacitance times VGS minus VX minus VTH times mu. I'm going to put sub n here because we're dealing with electron movements, times the derivative of the potential with respect to position, where the negative sign got canceled out by the negative sign on our relationship between electric field and voltage. Okay. So I'm going to do some math magic here, in as much as I'm going to move this dx over here and then integrate both sides. So we're going to integrate our current with respect to x from 0, which is effectively the left side of the channel, to the right side of the channel. And this is going to be equal to the integral of mu n C ox times W effective VGS minus V of X minus VTH dV of X, and we're integrating over the potentials, right? So on the, at X is equal to 0, the potential V is equal to 0 because we know that our source is grounded. And we're going to be integrating to VDS or VD, the same thing here because the voltage at our source is 0. So this is just the potential difference between the drain and the source. And so the result of this integration is going to be ID. So effectively, this ID gets moved out and this integral is just going to look like our effective length. And then I'm going to move that effective length to the other side of the equal sign so that I get mu n C ox effective width divided by effective length times VGS minus VTH times VDS minus 1/2 VDS squared. And this is valid for VDS is less than or equal to VGS minus VTH. So this is what our device current is going to look like when our drain source voltage, or the potential difference between the drain source, is less than what we call our overdrive voltage. So the overdrive voltage, effectively it's called the overdrive voltage because we're putting more voltage than is needed to turn the device on, to get it out of cutoff. So let me just say this really quickly. This quantity right here is commonly known as the overdrive voltage. And another thing, this quantity right here, mu n C ox, you might see this as K P. Actually, hold on. No. Kn prime. And then if we multiply that by the ratio of the width to the length, you might see this as Kn. So this is literally just a scaling factor for the current, effectively, that's dependent on the process by which the device is made, right? So in a batch fabrication process where all of the transistors are formed on literally the same substrate, they're all exposed the same amount of time to an ion beam or whatever, they're all going to have the exact same carrier mobility, they're all going to have the exact same oxide capacitance, all of that kind of good stuff. So this is usually just going to be given to you as some number measured in traditionally microamps per volt squared. Okay. So might be 200 microamps per volt squared, might be 5 microamps per volt squared. It literally just depends on the fabrication process of the device. The ratio of the width to the length is something that we have control over if we're designing integrated circuits, because we map out all of that kind of stuff. So we can get large device currents if we make our devices very, very wide with very, very short channels, which has its own effects, called literally short channel effects and all of that kind of good stuff. The threshold voltage is dependent on how much we dope our substrate, which is usually part of the fabrication process, and we don't get a whole hell of a lot of control over that. So like if you were to look up the parameters for, let's say, onsemi's C5 process, it'll tell you the threshold voltage for NMOS transistors is probably about 0.7 volts, and the threshold voltage for PMOS transistors would be listed as probably negative 0.9 volts. We'll talk about why there's a negative sign there in a little bit and all that kind of stuff anyway. So really, as a designer, the only thing that we have control over, at least from an integrated circuit perspective, is the ratio of the width to the length As a discrete circuit designer, we're effectively just saying, well, we need to pick a particular device that has a good mu-n-C-ox relationship that we can use for whatever application that we're looking at. All right, so this is a good stopping point for today. One last thing that I want to introduce here is that this condition is what we call triode operation. So triode doesn't really mean anything having to do with an actual MOSFET device. This is literally an artifact of using vacuum tubes as transistors. And the behavior here is similar to how a vacuum tube behaves when only 3 of the 5 terminals, I believe, are energized. So it's triode. And then what we're going to talk about on Monday is analogous to pentode operation of a vacuum tube. All right, that's enough ranting about physics out of me for today.